So welcome to the structural solution by our own colleague, Blaine Lawson. He will be talking about differential inequalities and generalized pluripotential theories.
Thank you very much. It's a pleasure to be here. It's a pleasure to have you all here. Sergey's abstract is a lot more interesting than mine. Started off talking well now. Anyway, some years
use reverse psychology.
Yes. So all of this is going to be joint work with Riesz. Many years ago, we were thinking about we came up with these calibrated geometries, which were, in a way, generalizations of Kähler geometry, in the sense that they produced lots and lots of volume-minimizing subvarieties. And I'm fine, thank you.
Okay. They sent me in the shop.
No, I'm in the shop.
I'm just going to here.
And at a certain point, many years later, we discovered, and I should say it was always a little upsetting because we never had analogs of holomorphic functions in these geometries. And pretty much it looked like they just didn't exist, nothing so wonderful as that. But we did discover that there was a complete analog of pluripotential theory, the pluries of harmonic functions, which are extremely useful in complex analysis. And so we started to investigate this, and it's nice. It gave us a kind of pluripotential theory on all calibrated manifolds, and Lagrangian geometry, and so forth. And then it turned out that, in fact, the story was much more general than that. These things appear in tremendous generality, and that's the story I want to talk about today. So I'm going to start with something extremely simple. Namely, I'm just going to take a subset, a closed subset, of the space of symmetric n by n matrices. And think of this as a constraint set. Okay, and then we fix an open set of domain in Rn. And we make the following definition that if you have a function which is twice differentiable, U's domain, then U is said to be F subharmonic if the Hessian of U at every point has an F. Pretty general at the moment. It's any closed subset. And what you'd like, so let me write down some examples. I'm going to keep the examples running, so maybe I'll do this over here. So one example is, obviously, you can look at all the matrices whose trace is bigger than or equal to 0. Okay, so I'm going to call this script. Another example is just all the matrices which are non-negative. These are symmetric, right? So all the eigenvalues are non-negative. And another one is, and I'm going to call this script G. Another one is where you're in Cn, complex n space. Then given a symmetric matrix, you can take its Hermitian symmetric part and require that be non-negative. And I'm going to make that like this. The Hermitian symmetric part is just A minus J. Every symmetric matrix can be written as this plus the same thing with a plus. And this guy commutes with J. J is the almost complex structure. And if you put a plus in here, it anti-commutes.
So there's a piece of notation missing. What do you want on the left-hand side?
I want this, the AC. Yeah. And there's another cousin here, which is, if you're in a quaternion n space, you can do the same thing. I'll write this way. And here, this is 1/4, and here you put A, and then I, J. And this is the guy that commutes with I, J, and K, all of them. So I think of this as the Hermitian symmetric part. And this is when you're in quaternion space. And there are lots more. Of course, you can write down almost anything. For example, you could take the trace of the arctangent of A and require that be bigger than or equal to some constant. This is something that comes up in special Lagrangian geometry. This is special Lagrangian potential equation. All right, so now the whole idea in potential theory is to get beyond the C2Ks to functions which are more general. Okay? And in particular, what you'd like to do is to get an extension of this notion to upper semi-continuous functions. And in fact, I want the upper semi-continuous functions to be possibly negative values. So this is a map into the real numbers union minus infinity. U is upper semi-continuous. So you remember, upper semi-continuous is jumping up continuous. You take the limb sup as you go into the point, and the value has to be bigger than or equal to the limb sup. And all right, so this is possible, and it all comes from viscosity theory, which was pioneered by Crandall, Ishii, Lyons, Craig Evans, and a number of other people. It's been an extremely successful theory. And here's how you do the extension. So first of all, I need it's a standard thing when you want to extend these differential notions to non-differentiable functions to have test functions, which do have derivatives. And so I'll start off with something which is upper semi-continuous, and then I'll say that if I have a C2 function, this is the test function for my given function u at a point x. So it's a test function if u is less than or equal to phi near the point, and it's actually equal to phi at the point. So in terms of the graph, if this is your function u, it doesn't have to be differentiable, but any function like that is a test function. There could be lots of them. Now, of course, there may well not be test functions, which is true for something like the absolute value of x if you look at it here. Okay. But so not every point has test functions. But nevertheless, we then say that u is f subharmonic if for all points in the domain, f subharmonic on the domain, and for all test functions, phi for u at this point, x. The second derivative of the test function is in. So all the test functions have to have their Hessians in this constraint set.
So this is back to this, there are no test functions.
This is automatic if there are no test functions. Okay. So this is satisfied if there are no test functions. So it seems a little silly, but it actually works. It's the genius of this, it really works. So the set of these things is going to be denoted by f of omega, set of these, the set of f subharmonic functions. And now, it turns out, in order to claim that this really is an extension of this naive definition in the C2 case, you need a condition. And the condition is that whenever I add a positive semi-definite matrix to F, you remain in F. And this is a certain weak ellipticity condition or positivity condition. And it's satisfied by all of these, and it will be satisfied by all the many other examples I'm going to write down. But but what's interesting is that this set has a lot of properties. So in particular, if you take any two functions which are f subharmonic, then the max, the pointwise maximum of u and p is in. It's also true that decreasing limits, uniform limits, stay. It's closed under taking decreasing limits. It's closed under taking uniform limits. And one of the key properties is this: that if you take any family which is locally bounded above, and then you form this function. You take the soup over all u in the family of u of x. Okay, just take the pointwise soup over the family. It's a mess. And then you have to take the upper semi-continuous regularization. This is again. So you probably all remember this from one complex variable when you studied the Perron process. This is the Perron solution to the Dirichlet problem. Okay? Where you're looking at this family of functions. But it holds in its enormous generality. All these properties are true.
What does upper semi-continuous regularization mean?
You replace the value of the point with the lim sup as you approach the point. And that turns out to be upper semi-continuous. So you can do it to any function. You can replace it with its kind of, it's the infimum of, it's the lower envelope of the continuous functions that lie above it. So it has all these, this family has all these wonderful properties. And now, let me make a point here. If you go back to these examples, then, so in these examples, what happens when you take this family for this subequation, the subharmonic subequation? Well, you get exactly the subharmonic functions. And I mean by subharmonic functions, the functions that on any compact set, if they're less than a harmonic on the boundary, they're less than the harmonic of the interior. It's one of the many, many characterizations of the subharmonics. You can also characterize them in terms of distributions because this is a linear inequality. They're all the same. You get exactly the same whole family. So these are the subharmonics. These are exactly the convex functions when I use this definition. You precisely get the convex functions by any of the equivalent definitions of the convex function. The restriction to every line is convex.
Just a little question.
Mm-hmm.
When you add p, what does that mean, say, in the Cn case?
Well, so it means that if you take a plus something which is positive, this should again be positive.
So the p is actually living on R2n.
Yeah, p lives on R2n, but when you take something which is positive semi-definite, this is also positive semi-definite. The Hermitian symmetry of Oxford. So, yeah, and so these are just the convex functions, and these are the classical plurisubharmonic functions, which there is this wonderful theory. It goes back to Oka and Grauer and so forth. Precisely this. These are the functions whose restriction to every complex line are subharmonic. Is. Okay. And these are the quaternionic plurisubharmonic functions. these undifferential effects. Okay, now hidden
Is there a
behind
harmonic theory associated to every subharmonic theory?
is there a harmonic theory?
Associated to every subharmonic theory. These are like generalized subharmonic theories.
Yeah, that's exactly what I'm going to talk about now. Yeah, there's an equation that underlies all of this.
Okay.
Yeah. So there is a partial differential equation, and you can say what it is in terms of the original definition. So here we have this definition, and I'm going to say that if I have a function which is C2, then I'm going to just call it F harmonic. And it's just it. If in this case the Hessian view lies in the boundary of that for all points in the domain. So if you come back and you look at these examples, the boundary of this set is just where the trace is equal to 0, and you have Laplace's equation. If you look at what it means here, so this gives you the Laplace equation. If you look here at what happens, well, this condition means that all of the eigenvalues are greater than or equal to 0. And if you're on the boundary, at least the smallest eigenvalue has to be equal to 0. That's the boundary. And that means precisely that the determinant is equal to 0. So this is the homogeneous Monge Ampere equation. This is the complex homogeneous Monge Ampere equation. And this is the quaternionic homogeneous Monge Ampere equation. Okay. This one has been, these have been studied by manifold people. This goes back to Alexandrov. This has been, the really significant work here is due to Dirichlet and Taylor in this homogeneous case. And Alexer and Verbitsky have done a lot of work on this Monge Ampere equation. Okay, so
I'm confused about that. That's a closed set?
yeah, it's a closed set. It's always a closed set.
What?
Yeah, it's supposed to be a closed set.
What's the boundary of a closed set?
The topological boundary. Now, is this
Points
condition
are not
which
in the
means
interior. I see. Points are not in the interior.
this condition implies that the set is the closure of its interior.
Oh.
So it's nice. This puts a lot of regularity into the set.
I see. This gives you something.
Yeah, I mean, you've got some crazy set, but it has all these open cones and so on.
Well, that's under this condition.
Under this condition,
You have a PDE.
right?
Okay.
Yeah, you've got a decent PDE. Well, I mean, it could be pretty bad.
So I guess this is the equations that come out are like homogeneous Monge Ampere equations. The question that Dennis was asking is if they're like harmonic functions, polyharmonic functions. Those would be things that where I guess u and minus u are both pluri. So you could look at it. There's a different kind of more linear PDE that.
Well, that's what I'm about to say. But in order to do this, you have to. Okay, so the question is, can you do an extension of this harmonic notion to and the answer is yes, but for this you need, again, you can use viscosity theory, but you also need duality. So let me say what that is. So my function is so suppose I'm going to say that an upper semi-continuous function on omega is F harmonic if and only if, first of all, I want you to be F subharmonic. And then, as Claude was indicating, minus u should be not f subharmonic, but f tilde subharmonic, where f tilde is the dual subequation. It's minus the complement of the interior of the f, which is the same thing as the complement of minus the interior of f. So, for example, if you think of script p as something like a positive quadrant, where the eigenvalues are positive, then the dual subequation, you take the complement, and then you take minus it. So the complement is to these three quadrants, and minus it becomes these three quadrants. And notice that this is again a subequation. If you add, whenever you add p, you stay in it. And so, and it turns out that if you do this twice, you get back where you started. It really is a duality. So this is actually a subequation if and only if this is, and so the whole theory of the subharmonic theory applies, and that's what I'm mainly going to focus on today. But I should point out that there are lots and lots of harmonics, so that these equations are terribly degenerate, but you can solve the Dirichlet problem.
So I was going to ask next, does Perron's method work? Does Perron's method work?
Yeah, to solve the Dirichlet problem?
Right.
Yeah, right. I mean, you got to work at it, right?
Yeah.
But it really is solved. Perron's method solves the Dirichlet problem in this and many associated things. So here I'm going to take a bounded domain in Rn, the smooth boundary, and both f and f tilde strictly convex. Now, I'm not going to spend a lot of time saying what that means. One way of saying this is that there are local defining functions which are strictly subharmonic, but you can also express this in terms of the second fundamental form of the boundary. It's purely geometric. Okay. Domain, and you look at the second fundamental form, and here you take any arbitrary, well, you look at this matrix with respect to splitting of Rn like this. This is the second fundamental boundary. This should be an F for all t very big. Okay. But whenever that's true, the theorem is that for every function which is continuous on the boundary, there exists a unique function, capital H, so that H restricted to the interior is F harmonic, is actually a solution, and H restricted to the boundary is a classical Dirichlet problem. But you can do this for any of these really, really weird sets. Now, the boundary of F doesn't have to be nicely behaved at all. It's just, and the equations are now can be completely degenerate. I mean, these are degenerate equations. You don't get much regularity if you don't assume something about the regularity of the boundary values.
What is an F harmonic function in a convex case?
An F harmonic function in the convex case is a harmonic function. So
it's not linear.
No. I mean, you should think of something that has lines in it. Okay. I mean, so a nice example is you take the function on the boundary of the sphere, and then take the cone on it. And because you've got these cone lines, they correspond to. And morally, you often get these lines in the solutions. There's some Monge Ampere equation. Okay, so
what's the one where you said you didn't get much regularity? I can't read that.
Oh, you don't get much regularity in any of these three unless you make some assumptions about the boundary. So, even then, you don't necessarily. Okay, so now I want to write down a few more examples. So let me do that. Just to So here are some. So the first one is what's called the Hessian equation. And this is where you require that the first k elementary symmetric functions of the eigenvalues of A be greater than or equal to 0. And the boundary of this dissociative equation is where this is equal to 0. When k is equal to 1, we get this guy. When k is equal to n, we get that guy. And these are somewhere in between. So these have been much studied by people like Schrödinger and Wang and Wooten. And there's a huge literature on these things. The one that I really like is the following. You take a compact subset, closed subset, of the Grassmannian and p-planes in R. Okay, and you write down the following set. This is equal to the set of A that has the property that the trace of A restricted to W is greater than or equal to 0 for all of these distinguished planes. So this is some compact family of p-planes, and you ask that the trace on every one of these p-planes be greater than or equal to 0. Okay? If, for example, you start with the set of all lines, real lines, it simply means that you're here. If you take all the complex lines, you get this. But it can be much, much more interesting. Well, you can start, for example, by just taking G to be the complex Grassmannian of Q-planes in Cn, which is a subset of the Grassmannian of 2 Q-planes in R-G. And this gives you something called Q-convexity, geometric Q-convexity for functions. This is something that's been kind of standard part of several complex variables for quite a while. Even more interesting, you could take an algebraic subvariety of this creature, and you've got yourself a differential subequation. It's not so clear what the equation is, but it's nice. Then you can also take.
So that wouldn't be satisfying your condition about adding p's.
Oh yeah, that's automatic. That's automatic in this case.
It's automatic?
Yeah, it's automatic. If you had something positive, restriction is positive, and so the trace just goes up.
The restriction.
The restriction, yeah. Restriction of anything positive to a subspace is always positive. Because the condition is just that it's positive on every vector. And now you could also, in Cn, you could look at the Lagrangian planes It's an interesting case, for example. So what's it mean to be subharmonic in the sense that the restriction to every Lagrangian n-plane is a real subspace is positive? Or, if you're familiar, you can also look at calibrated planes. So, for example, if you know a little bit about calibrations, you could look at the associative planes, 3 planes in R7. These are the guys that are the imaginary products of quaternion subalgebras, and they give you this beautiful family. Okay, so now there's a few more examples. Because I'm going to be coming back to this. So you could have an F which is ON invariant. Right, so the orthogonal group acts by conjugation on symmetric matrices, and you can ask if this subset be invariant. And what that means is that F is given by conditions on the eigenvalues, in fact on the ordered eigenvalues of that. Right, the complete set of invariants are the eigenvalues of the matrix. Okay, so for example, it's positive if the first eigenvalue is greater than or equal to 0. But you could also look at something like lambda k greater than or equal to 0. K. So whenever you have an orthogonally invariant equation, and it can be pretty strange, eigenvalue space, there are counterparts, FC, FH, which are given by the same condition on the eigenvalues. So when you take the Hermitian symmetric part, suddenly you get something which commutes with complex multiplication, so the real eigenvalues come in pairs. The eigenspaces are complex lines. Again, you have essentially n eigenvalues, and you put exactly the same conditions on them. And so this guy is just a complex analog, or a complex counterpart of this. This is where the first eigenvalue is not 0, and this is where the first complex eigenvalue is not 0. Now, finally, getting around to this other equation that I really want to talk about for a little while. And that's, I'm going to take p to be an integer greater than or equal to 1. I mean a real number bigger than or equal to 1. And so this is going to be in terms of the ordered eigenvalues. You take the first eigenvalue of A, and you go up to the integer part of P. Take that eigenvalue, and then you take a little piece, namely precisely P minus integer part of P times the next eigenvalue. And you want that sum to be greater than or equal to 0. You know, why? You don't need to be told this at 4 in the afternoon. But, so I'll try to justify this, but let's take the case where P is an integer. Then this is just the statement that the sum of the first ordered eigenvalues is greater than or equal to 0, which is equivalent to the fact that the trace on every P-plane is greater than or equal to 0. So it's one of these geometric guys where you take the whole Russell and when P is an integer, these have very, very nice synthetic characterizations. They're the functions whose restriction to every P-plane are standardly subharmonic, under the Y and under the harmonics. And the restriction to every minimal P-dimensional submanifold is always, they're always subharmonic in the Laplace-Beltrami sense. Okay. All right, so this brings me to something called the Riesz kernel. And this is Embry's. So this is a function of Rn, and it's defined as follows. It depends on what P is. So it's minus 1 over norm x to the P minus 2. If P is bigger than 2, it's the log of x if P is equal to 2. So you're looking at if P were really the dimension of P was equal to n. You're just looking at the Newtonian kernel, right? The fundamental solution for the Laplace operator. But here I'm letting n be big with respect to. And then the final case is going to be x to the 2 minus p if 1 is less than or equal to p is less than 2. And I think for the most part you should just think of this example. For one this case. All right, so what's so great about these functions? Well, what's nice about them is if you take the Hessian of this guy, it turns out to be up to a positive constant that I'm going to forget. 1 over x to the p minus 2. And it's always the same. I mean, they look very different, but their Hessians are precisely the same. This is orthogonal projection onto the complement of x. This is at a point x. Minus little p minus 1 times orthogonal projection onto a line generated by x. Okay? So another way of thinking about this is this factor. Oh, this is p. P. And here you get a matrix with a lot of ones, and at the bottom you get minus p minus 1. If you choose coordinates for which this is the x direction. Okay. This is a very simple matrix. Up to the scale factor, and if you choose coordinates so that x is the last coordinate, there's a lot of ones in this guy. Okay. So
this works for non-integer p?
Yeah. So now, all right, so the big thing here is that this guy is strict piece of p harmonic. It satisfies the equation outside the origin. And as a matter of fact, this subequation is precisely the smallest subequation for which this is true. You take these guys, and you take the kind of convex subequation for which this is true. All right, so now, given that, I can define the Riesz characteristic. So, at this point I want to make a simplifying assumption. And that's essentially from now on. I want to assume two things. F is a cone, vertex is the origin, and secondly, F is G invariant, where G is a subgroup of the orthogonal group which is transitive on the sphere. Okay, so it could be the whole orthogonal group, but it could be the unitary group or the special unitary group or the symplectic group. Okay. But it still leaves you lots of equations. All right. Then the Riesz characteristic of F is just equal to the sup of sup of numbers p such that 1, 1, 1 minus p minus 1 is in F. So here I've chosen some coordinates, but if it's true for one choice of coordinates because it's invariant under a group that acts orthogonal or transitively on the sphere, it's true for all. So you only have to check it. You just have to check one guy that looks like this. And then you have to take a max and soup over these things. Okay. So, I think seems I've erased all mine. So, the Riesz characteristic of this guy is n. The Riesz characteristic of this is 1. The Riesz characteristic of this is 2. The Riesz characteristic of this is 4. But if you look at more complicated equations, it gets more interesting. And by the way, it's it is easy to compute. I mean, it's, you know, it's not anything heavy. The Riesz characteristic of this sigma k is n over k. Is this Hessian equation. And the Riesz characteristic of script p is p. Okay. And if you take G now has to be invariant in the Grassmannian P planes in Rn, the Riesz characteristic is P. So for all these things, Riesz characteristic is P. Oh yeah, and if you take, if F has Riesz characteristic P and it's invariant under the orthogonal group, then it's the Riesz characteristic of the complex counterpart is 2P and the quaternionic part is 4P. Always. So that it's a complete generalization of the 1, 2, 4s here. All right, so now the first theorem on this kind of justifies the concept is a removable singularities result. So I'm going to assume that F is any subequation and M is a convex cone subequation with Riesz characteristic equal to P. And I'm going to assume that F plus M is contained in F. So this is a subequation which is monotone under this M, this cone. Whenever you stick an M cone in there with a vertex inside the subequation, the whole cone stays in there. And then the claim is that any set, any closed set of locally finite Hausdorff P measure, this is real, is removable. It's removable for subharmonics and for harmonics. I'm not going to write. So what do I mean by removable? I mean, if you've got a function, here's E, you've got a function which is subharmonic as a complement of E, and it's locally bounded at points of this exceptional set, then the upper semi-continuous extension is subharmonic across. And there's a similar statement for harmonics. Harmonics are any set of locally finite Hausdorff P measure.
How do you compute P?
P is a Riesz characteristic. So you take, it's the Riesz characteristic of this monotonicity set. So, all right, so now this brings me to some of the newer ideas. I talked about all of this before. So I want to talk about tangents. What are the tangents?
What is that for harmonic functions? The removal of singularity?
If you've got a function which is harmonic in the complement, is continuous, it has to be upper and lower semi-continuous. So if it's continuous on the domain and harmonic outside of E, it's harmonic on E.
Well, what's the Hausdorff dimension relevant here?
And E has to have locally finite.
What?
E has to have Hausdorff dimension P. In fact, it has to have locally
For classical harmonic functions.
Well, for classical harmonic functions, it's what, 2 of them. For classical harmonic functions, N. Yeah, N. That's what it says. That's true, right.
What's N?
Lebesgue measure 0. Lebesgue measure 0. Hausdorff N measure in R. Okay,
They
so
measure 0.
continuous. So we have a continuous function which is harmonic outside a closed set of measure 0 in Rn. And it's
I don't believe that's the plan.
what?
I don't believe that's the plan.
The classical rule.
Oh, I mean,
But it's continuous.
it's
Continuous functions.
Huh?
You called it continuous.
I know. I can make one. Just take the probability that you get a Cantor set on the Brook dimension. That's your harmonic function. It's 1 when you approach the set, and it's 0 on the boundary, as Dennis say. Okay.
No, I don't.
Singularity set supposed to be closed.
Close to the positive Brook dimension, which is a function which is 0 on the boundary of disk, and probability that hits the Cantor set before it hits the boundary. That's your function between 0 and 1. It's continuous. It's harmonic outside the set, and at the set it approaches 1.
Yeah,
And I think it can be positive. It has to be capacity 0 or something like that.
yeah, I guess that's right. Well,
Absolute value of imaginary
It can be said in terms of calibrated. Well, I think
Compact stuff.
I don't know. I mean, maybe P has to be less than in here. But anyway, let me go on because this is a really good point. So let me write down a flow. So if I give you a function which is subharmonic in a small neighborhood of the origin, and I take a positive number, then u sub r of x is the function. Well, it depends. So it's going to be r to the p minus 2 u of r x. If p is bigger than 2, it's going to be u of rx minus the sup on the ball of radius r of u p equals 2, and it's going to be u of rx minus u of 0 over r to the 2 minus p here in this range. Now, probably it isn't so important to know what the details are here, but what is important is that this fixes the Riesz kernel. Okay, the Riesz kernel, I've erased it, it's homogeneous. It's homogeneous at degree p, essentially. So a little bit funny when you get to the log, as it always is. Right? It's not homogeneous at degree 0, you've got to deal with the logarithm. This is an interesting case. And then we have to subtract this off. These functions, the Riesz kernel here goes to minus infinity. In this range,
So you're saying that this process sends the Riesz kernel to itself?
yeah, sends the Riesz kernel to itself. And now, what happens when you apply this flow as r gets smaller and smaller is that this guy is defined on a bigger and bigger disk. And so in the limit, you can hope to have something defined on all of Rn. And so a tangent, so u is a tangent to little u at the origin. If there exists a sequence of numbers, real numbers, coming down to 0, with the property that u sub rj converges to capital U in L1 loop of Rn. It's eventually defined when I'm big enough for any compact set. So this is a tangent to a function, but you just think of it as a blow up, right? It's a kind of blow up. And of course, I'm now considering f to have, I'm assuming it's f subharmonic, where p is the Riesz characteristic. Okay. So now what's interesting about this is that tangents always exist. So the first theorem is that if f is convex, or if the Riesz characteristic is in this range between 1 and 2, then tangents exist. And now I'm taking a limit in L1 lobe, but it turns out that the limit will always have a representative in L1 lobe, will always have an upper semi-continuous representative, which is, in fact, subharmonic. It's better than that. It's actually F harmonic, except it folds places where it's minus infinity. So this is nice, and it leads to the question of uniqueness. And
This one for all F subharmonic functions or F harmonic.
F subharmonic. Yes. Yes. F subharmonic. That's a very big difference. Every subharmonic function has tangents. And so you're going to write the set of tangents to U. So the U is F epsilon and F has the Riesz characteristic P. So this is the set of tangents. And so this, since you always have tangents, as many of you know, questions of minimal varieties and so forth, harmonic maps, the big question is uniqueness. And so what about uniqueness? Well, there are two definitions. One I'll call uniqueness. So uniqueness holds for the sub-equation F if for all U F subharmonic in a small neighborhood of the origin, the tangent space to U is a singleton. Only one. That's what uniqueness means, right? But it's now not just for the function U. It has to be true for every U. Every U is a unique tangent. And then there's something called strong uniqueness. Strong uniqueness holds for F if not only is it a singleton, but it's actually a constant times the Riesz kernel. A constant times the Riesz kernel, where theta is actually the density, which I'll talk about in a moment. So this is a predetermined number.
So in the definition of tangent, there's this, you have a chosen sequence to get a tangent.
For every sequence, there's a subsequence. Yeah, that's right. So there may be many, many. So this could be a big set. Just as. So in fact, let me point out that it can be a very big set. So let's look at basic examples. So I'll take script P. These are the convex functions. Here uniqueness holds. U holds. But strong uniqueness fails. Now the fact that uniqueness holds just has to do with the fact that when you're doing this dot, you have this convex set. So you look at its graph. The graph is a convex, well, the epigraph is a convex set. You take a point, you blow it up, and you get a unique limit, which is again a convex set, but it's a cone. Okay? And so uniqueness just follows from convexity theory, elementary convexity theory, but strong uniqueness fails like mad. So again, you take the unit disk and take up here a function which is C2 close to constant. Okay? And then take the cone on it. If it's sufficiently close to constant in the C2 norm, this will be a harmonic. So, and its tangent is itself. It's invariant under this. So that means it fails catastrophically. I mean, everything in the C2 neighborhood of the constants. Okay? And then you can pull this down. So that's not so good. Now, if you look at the plurisubharmonic case, it's even worse. It turns out that uniqueness fails. So, and in fact, it goes back to work of Chieselman that he characterized exactly what these sets could be. He put down 4 or 5 defining properties. Every set of plurisubharmonic functions that satisfy these properties is the tangent space. So, I mean, it's really crazy. So you have to come up with a function which is sometimes going this way, sometimes going that way. And so you have all these various limits. And so the same thing's going to be true for, this is going to be the same thing. So it looks bad, right? I mean, it looks as though there are no tangents. But to our surprise, the following is true. So here's a theorem. Suppose that F is O(n) invariant, and F is not equal to this convex equation, the real Monge Ampere. Then strong uniqueness holds. No matter how crazy the subequation is, the tangents are always a multiple of the Riesz kernel. Always. And not only that, the strong uniqueness holds for F and also for the counterparts. Remember that these complexes returning on the counterparts, it holds for them too. So, and now it also holds in a number of geometric cases.
So is the group still O(n), or do you make a substitution of a different group? You say O(n). F was O(n) invariant, but when you are making a statement about these other...
Well, the point is that if it's O(n) invariant, it corresponds to a certain subset of eigenvalue space. So you get some subset of eigenvalue space, that take that same subset and apply it to the permission symmetric part.
So I guess the thing that I was curious about, O(n) is acting on Cn or an Hn, the same n.
Mm-hmm.
It's the...
Mm-hmm. O(n) is acting on Rn.
It's not O2n. It's not...
No. It's O(n) invariant, and then...
I see.
And then...
Gotcha.
Yeah. So for Cn, is it odd to n?
I'm sorry?
No. It's just... so it's O(n) acts on Cn.
Probably Rn inside of Cn.
Yeah. And on its orthogonal complement.
Let me see, I'm not sure. I'm saying that if you... I mean, these are going to be unitarily invariant, right? You start with this condition on the eigenvalues, and it's just an eigenvalue condition. You look at that.
Right, so that's why I was asking, maybe the group is UN.
Well, I think the group is UN.
Okay, and SPN.
And then SPN.
Okay, yeah.
Mm-hmm. Yeah, the underlying group is UN or SPN. And all right, well, I think I'm out of time, and I had a lot more to say, but anyway, uniqueness holds, and now there's a notion of density and structure and density sets, and there's a whole very elaborate account which really applies in this general situation. That's it.
So, I mean, these are sort of, in spirit, like constant coefficient equations. You can make sense of them on manifolds of special polynomials.
You can certainly do that, but there's no reason why you don't need the invariance of the equation to talk about the Riesz characteristic. You just want to know that these particulars. You can ask something on a manifold. You can ask that a subequation be a cone at every point. And then you can ask that these particular matrices always lie in the boundary of the cone. That means that the infinitesimally, the Riesz kernels are harmonics. then you can blow up and look for tangents.
So, I mean, for example, if you have a manifold, a special holonomy, and the cone is chosen so that it's invariant under the holonomy group, then you could sort of parallel transport it to all points in the manifold and you have a built-in theory.
Oh, yeah, for sure. Yeah. And, so anything which is invariant under G, you have holonomy G or contained in G. Go ahead. Right.
So what about those ability theory when we have the bounding harmonic function, say, global harmonic
You want to know when bounded harmonics in this theory are trivial.
Yeah, not for all major exceeding bounding harmonic function is trivial.
Right.
But in your case, you might have something similar. You might have similar theory.
Well, yeah, I mean, certainly for lots of these sub-equations, that's going to be true. But I don't have a nice packaged answer to this question. I think it's an interesting thing to look at. When you've got the equation phenomenon or not.
For Harnack inequality.
Well, yeah, I mean, the Harnack inequality enters in a lot. And as soon as your sub-equation is convex, then the convex set is the intersection of half spaces, and every half space is a sort of conjugate of the Laplace operator. So you get lots and lots of Harnack inequalities whenever it's convex. But the interesting thing is when the Riesz characteristic is between 1 and 2, not equal to 2, every harmonic is actually alpha ultra-continuous, where alpha is 2 minus p.
So that again, every harmonic is what?
Every subharmonic, if 1 is less than or equal to p is less than or equal to 2, every subharmonic is alpha, which is 2 minus p, ultra-continuous. And the tangents are actually limits in the beta Hilbert norm for beta listen. So it's in this range, everything is different. It's kind of nice that singularities are finite.
That's an example.